In this chapter, we're going to start talking about the different types of chemical reactions and then how you actually write out chemical reactions and how they work. Okay, so a lot of this first part is review from stuff that we did in last semester, but so we're just going to run through it pretty quickly here. So a chemical reaction happens when substances go through chemical changes. So this is going to take one substance or a couple substances and change them into others. Okay, so you are actually going to get one chemical substance changing into another through this reaction. Signs of a chemical reaction: you have formation of a gas, formation of a solid, or a release of energy or light. Okay, so those are some relatively easy signs of a chemical reaction. So chemical reactions, they're not going to create or destroy atoms. They're not going to add in different atoms that are not involved in the equation, in the reaction. They're just going to rearrange the atoms in those compounds involved. So they will break bonds, okay, between different atoms and then form other bonds. So you have the reactants, which are the substance or substances that participate in a chemical reaction. And you have your products. So those are substance or substances that are created through the process of the chemical reaction. So here we have our reactants, isooctane and oxygen, okay, and they are reacting to form carbon dioxide, to form carbon dioxide and water. And then you're also going to get a release of energy. Okay, so that might be in the form of heat, it could be in the form of light, or could kind of combine the two and fire. Okay, so it is some form of energy release. So that is your visible sign that a reaction has taken place here. So chemical reactions are always going to involve some type of change in energy, whether that's releasing energy from the compounds or pouring energy into the compounds. Okay, so breaking bonds is going to require energy. Right, so I think last time we talked about this, I used an example of breaking sticks over your knee. You actually have to use some energy in order to break them. And it's the same kind of idea with breaking chemical bonds. In order to form them, you're actually going to release energy. Okay, because that takes the atoms down to a lower energy state and allows them to kind of be happier. So they release that excess energy that they no longer need. So energy is going to be conserved in all chemical reactions. You're not going to create or destroy any energy. So the sum of the energy, the sum of the energy entering the chemical reaction is going to equal the sum of the energy leaving the reaction. Okay? So you're never going to have more energy on one side of your reaction than on the other. It's always going to be equal in some way. Okay, not always found with the same atoms or in the same type of bonds, but they will be equal on either side of the reaction. So chemical energy is the energy that is stored in the form of chemical bonds. Okay, it is basically another way of referring to chemical bonds, but referring to the energy side rather than kind of the physical side. So different compounds will hold different levels of chemical energy. So gasoline fuel holds a lot. Other fuels will also hold quite a bit of energy. Things that can burn relatively easily generally have quite a bit of chemical energy that the burning, the spark, basically just gives them a way of releasing that energy. And that's what causes the light, the heat, the fire. So chemical energy, when it's released during a chemical reaction, can then be converted into another type of energy. It's actually how we run cars, is we use gasoline, basically lighted on fire, and then use the energy that's released from that chemical bond in order to propel a car. That's a very simplistic way of going through that, but in general terms, that's what's going on in a car. It's why it's called a combustion engine. So you have really two different types of reactions when you're talking about the energy of the reactions. So you have exothermic. So exo is going to release energy. So way to remember this is exo, exit. Okay, so it's exiting the reaction. The reactants will have more energy than the products. So the energy, oh, sorry, I don't know why I'm yawning so much, but the energy is often released as heat or light. So if you have a reaction that's getting really hot, it's a good bet that it is exothermic. So energy will generally need to be put in to start the reaction. So that could be the ambient temperature in the room, it could be body heat, it could be a flame. Okay, so something needs to be put in to start the reaction. And that is known as the activation energy. So it's the amount of energy needed to kickstart that reaction and get it going. So examples of exothermic reactions, you've got freezing, condensing, and combustion. Okay. So in all of these, you are actually releasing energy from the reactants. Freezing, say if you were freezing water, the water is going from liquid form where it has a relatively high amount of energy, and then it's freezing, causing it to go into a solid where it's a lot more constricted, it can't move around as much. And so it's releasing that excess energy that allows it to move. Same kind of idea with condensing. And then combustion is basically just, sorry, water's going nuts. Combustion is just, it's basically a fancy term for burning something. So it's burning something and it's releasing the chemical energy in order to feed the fire. So if you look at the way an exothermic reaction looks, okay, here we've got our chemical energy right here and the time of the reaction. So basically the progress through the reaction here. So you can see reactants here have a relatively high chemical energy. You're going to have to feed in the activation energy to go up. And then at this point, this is when the reaction is really kicking off. And so then all of a sudden it's going to drop in energy and you're going to get the products. So the key thing with this, with an exothermic reaction, your reactants are going to be higher up than your products. Okay, so this is going to kind of look like a pretty good roller coaster where you go up and then you're just going to go down and go off. Okay. Next up, we have endothermic reactions. So endothermic are the opposite of your exothermic reactions. Endothermic are going to absorb energy. Okay, so in, okay, that's the way I remember it. So products are going to have a higher energy than the reactants. So when you look at the same type of graph, you'll notice that it's basically flipped. Okay, so we had our reactants here, okay, relatively low energy. They absorb a bunch of energy in order to kickstart the reaction, and then the products are at a relatively high energy, so there's not a whole lot released after the reaction starts. So this would be kind of a bad roller coaster. Spend all your time going up, 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 finally get to the top, and then it's just kind of like, we're done. Okay? So examples are basically the opposites of what we just looked at with exothermic. We have melting, boiling, and photosynthesis. So these are all reaction types that are absorbing energy, either from their environment or from sunlight or something like that. Okay, so a chemical equation, we're going to get more into these in the next section when we actually work on balancing them. But chemical equations use atomic symbols to represent a chemical reaction. So it's going to show the relationship between the reactants and the products. So you're going to have the reactants on the left and the products on the right. So you're going to use the subscripts and coefficients. Subscripts will be after each individual atom or each individual element to tell you how many atoms of that type you have in the compound. Coefficients are going to go in front of the compound and tell you the number of each of those reactants or products in the chemical equation. Okay, so you may have seen, let's see, give you a quick example of a chemical equation. You have the chemical equation for photosynthesis. Okay, you have water and carbon dioxide coming together to make oxygen and glucose. Okay, so the subscripts here, let me get back to here. Okay, so the subscripts are the smaller numbers that are underneath the elements. Okay, so we have our atomic symbols. H stands for hydrogen, O is for oxygen. The 2 here tells us that we have 2 hydrogens in this compound with this oxygen molecule. Okay, now this is a coefficient, this giant 6 here. It's going to come before the compound, and it's going to tell you that there are 6 H2O molecules in this reaction. Okay, so there are 6 water molecules needed to react with 6 carbon dioxide molecules in order to produce 1 glucose molecule. Okay, as well as 6 oxygen molecules. Okay, so that's the difference between subscripts and coefficients. And then if you ever see, I don't have my pen. Give me a second. If you ever see a superscript like this, where it's a small number but it's higher up, that is the charge on the compound, the ion, whatever it is. Okay? So, just a couple little terminology type things there to help you remember what the different terms are. So reactants, again, are always going to be on the left of your reaction, and then your products are always going to be on the right. And they will be divided by this arrow. Okay? There are various different types of arrows that scientists will use when writing out chemical equations. It's weird that there are multiple different types, but they all mean the same. It's telling you which way the reaction is going. Okay, it's telling you, it's pointing from the reactants to the products. Okay, so this is just an example of a chemical equation. We have methane and oxygen reacting to yield carbon dioxide and water, right? And this is what happens with if you have a gas stove. Okay, you light that and you can see the little blue flames flying out here. Okay, so that's what's happening there. And then if you were to write this as an actual chemical equation, okay, methane is CH4, so you have 1 carbon, 4 hydrogens. You only have one of these compounds. And then you have 2 oxygen molecules. Well, each oxygen molecule has 2 oxygen atoms, and there are 2 of these oxygen molecules. And then once these 2 react together, you form a carbon dioxide, which is 1 carbon and 2 oxygens, but there's only one of them. And you also form 2 hydrogen molecules. So this 2 right here tells you that there are 2 hydrogens, 1 oxygen, but there are 2 of these compounds. Alright, so we're going to break here and then pick up with the different reaction types from the physical side instead of the energy side in the next video.